Loading. Boom. All right, problem 2047, remove nodes from linked list. Let's go ahead and get right into it. So you're given the head of a linked list, okay? It's a pretty standard linked list. Linked list is a data structure where you have a node, and the node has a reference to some other node you call the next node, okay? Remove every node which has a node with a strictly greater value anywhere to the right side of it. Return the head of the modified linked list, okay? So if you're given a linked list like this, where it's 5, 2, 13, 3, 8, so 5, 2, 13, 3, 8. You know, your node, your system has links like this when it's given. Now, if a node has something that's strictly greater than it to the right, then you want to remove that node from the system, right? So 8 is going to stay, but because it has nothing strictly greater than 8 to its right. 3 is going to get removed because 8 is to its right and 8 is greater than 3. 13 is going to stay because 13 has nothing greater than 13 to its right. 2 is going to get removed because it has 13 and 8, which are greater than it to its right. And 5 will be removed because it has 13 and 8, which is greater than it to its right. So the final tree is, after we remove these nodes, is just 13 and 8, right? Simple enough. So how do we process this? Well, before you can make a decision about a node, right? Before I can make a decision about a node 2, I have to have traversed all the nodes that are to the right of 2, right? Before I can make a decision about keeping a node or discarding a node, I have to have information about everything that comes to the right of a node. So we're going to do a recursive solution. And we want to look at everything that's to the right of a node before we process a node. So that means we're doing a post order traversal, right? Meaning that we traverse everything, traverse the remainder of the tree, and find the max. Then we make a decision about the node we're looking at. So if we looked at this tree, what we would say is, well, let's look at it in terms of a post-order traversal. So let's copy it. So why is this? You gotta be kidding me. So let's copy this. Why is that happening? Whatever. So we'll just look at it here. So before we make a decision about 5, well, we can't make a decision about keeping 5 until we know what comes to the right of 5. So we have to look at 2. Before we make a decision about 2, well, we need to know what's to the right of 2. So we have to make a decision about 13. Before we make a decision about 13, we have to, I don't know why I'm numbering these. We have to make a decision about 3, right? Before we make a decision about 3, we have to make a decision about 8. Before we make a decision about 8, well, there's nothing else to look at. Now, when we go back, we need to provide the maximum value to the nodes that come before, because that value, the maximum value, since a node is removed if there's a value that's greater than it to its right, that would mean that the greatest value to my right is the only value I have to look at, right? Because the greatest value to my right is the one that could remove me. Anything less isn't worth looking at, because if the greatest one will remove, right? If the greatest value, like for 2, okay, if I'm looking just at 2, what makes it such that 2 is getting removed? 2 is getting removed because 13 and 8 are to its right. Correct? Because these are both greater than, well, actually, 13, 3, and 8 are causing it such that 2 is getting removed because there's a value that's strictly greater than 2 to the right of 2. But we don't need to consider 3 and 8, right? Because if something smaller than the maximum value is causing a node to be removed, then something that's greater than that value is also going to cause the node to remove. So we only need to look at the largest value to the right of a node to determine if we need to remove a node, right? Because any value larger than a node value will cause that node to be removed. So you only need to look at the maximum value because that maximum value is the most likely, right? It's the biggest thing, so it's going to be the thing that gets the system removed. Okay, so when I look at the system, right, I traverse down this thing and I got here. I make a decision about 8. Well, since 8's alone, 8's going to be kept, right? And we'll say, okay, well, the largest thing I've seen so far on the way back, so when I return from this recursive call, I say the largest thing I've seen is 8. And now I can look at 3 and say, okay, the largest thing is 8, and I'm looking at 3. Well, 3 is less than the largest thing, so there's a value that's greater than 3 to the right, so 3 gets removed. And the largest thing is still 8, so we bring back 8. 13, the largest thing to the right is 8, so the largest thing is smaller than me, so that means that any subsequent value that's to my right is smaller than that. So if the largest person to my right, if the largest person in Arizona, if the tallest person in Arizona is shorter than me, that means that everybody in Arizona is shorter than me. That's the idea here, right? If the largest value to my right is smaller than me, that means that every value to my right is smaller than me, right? So when I compare 13 and I say the largest value to my right so far is 8, and that's smaller than 13, so that means everybody to my right is smaller than 13. So that means 13 is going to get kept, but now this value will get changed to 13. And then we play the same game with 2. Nope, it doesn't work because 2 is less than 13. The largest value to the right is still 13. Ugh, I'm getting my colors mixed up here. 13. And then 5 is less than 13, so this also gets removed. So when this system is done, it just returns 13 and 8. Okay? So now how do we rebuild this tree? Because, right, the starting tree is this green link, but now we have a tree, the final tree is like this 13 to this 8. So what you should do when you return is you need to save information about, you know, the largest thing as you traverse, as well as the tree that exists, right? When we are here, if we don't keep a node, we return what comes next, right? So when this thing gets returned, it'll be returning 8. And then when it gets here, it's not going to add 3, so it'll return 8 again. When it gets to this node, 13's included, so we return 13 and 8. When we get to this node, 2 is not included, so we return 13 and 8. And we get this node is not included, so we return 13 and 8. So basically, you only include yourself in the tree that's returned if you are less than the maximum that you found so far. Okay? Otherwise, you don't, you just return what's left over. So we'll make a helper method to do this, which takes in the head. If it's not a head, that means that the recursive call is done, right? Just like when we got here. When we got to this system here, right? When we got to this call, when there was nothing else to look at, we just returned nothing. Otherwise, we'll call the helper on the remainder of the tree, right? So that will say, like, when we call here, we'll set this next node to whatever's returned from this entire system. Okay? Well, let's clean this up just a little bit because it's a little crazy. And that, as a consequence, will essentially create this system that we're considering, right? So I'll set my next node to whatever the solution to this problem is, right? I'll set this next node to whatever the solution to this problem is. I'll set this next node to whatever the solution to this problem is, right? So when this is done, when this recursive call is done, it'll return 8. So you'll have the system 3 and 8. Now, since 3 isn't included, you'll return just 8. So this 8 will come back, and 13 will attach itself to this 8 because that's what's returned from the function. So you'll have 13, 8. Since 13 is a part of the solution, 13 and 8 gets returned back. So then 2 attaches itself to 13 and 8. But since 2 is not a part of the solution, you just return 13 and 8. So 5 will attach itself to 13 and 8. But since 5 isn't a part of the solution, we'll only return 13 and 8. So we're going to end up having all these additional pointers, but we'll only return the information that needs to be returned. And that way, you know, the solution will look a little strange. Like if you actually look at the linked list that we end up creating, it'll be a little strange, but we'll make sure that we only return the information that pertains, right? So the sub-solution goes to head.next, and we'll set head.next to that. And then we'll have to make a decision, right? If the head's value is less than or equal to whatever is the greatest value, greatest to right, let's call it max val. That means we include it, right? Because it means that the head value is greater than or equal to the max value, actually. So if my value is larger or equal to anything to my right, then I keep it. So that means I just return the head. But if my value is not greater than or equal to anything to my right, then I return head.next. So I don't include this value, right? I return the sub-solution, right? When we got here, we got to this point, right? When the max value was 8 and we were looking at 3, right, we're going to end up having this system as a solution. We don't include 3, so we include 3.next, which is 8. So this gets returned to 8. 13 attaches itself to 8, right? Because that's the solution that's, whoa. Because that's the solution that's, what have I done? That's the solution that's returned, right? Because that's the solution that's returned. So the solution that's returned, which would be 8, 13's next becomes 8. And then since 13 is the solution, we return the 13 solution, right, which is this. Okay. So then how do we calculate the max value? Well, what you can do then is just create this little system that exists with inside, which starts as float negative infinity, because the initial maximum value is nothing. And every time we traverse a node, we'll just reassess what the max value is. And then now that we've done that, we can just run this helper function on the head. And then we hit submit and we pray. Sometimes I just sit and pray. Sometimes I just sit and pray. Oh, so it's got to be self.max value since I define it that way. And there you go. All right, so what's the runtime of this? Well, it's constant time. I mean constant, not constant time. So it's end time, right? Because we have to go through each node, and we only go through each node twice, right? Because we go through the node in this direction till we get to the end, and then we have to go backwards in this direction to process each of the systems in reverse. And then that's going to take end space, right? Because we create the stack, and we have to go through the stack to process each of the nodes, and then we have to pop from the stack. So we have n time to go through and come back. And then we have n stack space because we have to create a stack frame for each of these nodes when we traverse. So O of n time, O of n space. All right, guys. Thanks.